A highly regarded methodology used in design, engineering, and business fields to promote business fields is known as design thinking. As shown here, design thinking consists of 7 interrelated phases. The first 3, understand, explore, and define, involve developing a deep understanding of the impact of the design. Included at the top of the list are the vast bodies of scientific concepts that govern the natural world. Scientists and engineers in the rapidly growing field of nanotechnology need to understand the biology of organisms at a molecular level. For example, scientists are investigating ways in which an ingredient of bee venom can be delivered to cancer cells through the bloodstream using small nanoparticles. As demonstrated in the technical videos, you will see how 123D design software can help anyone, regardless of their prior artistic or technical background, engage in the process of ideation. These same tools will enable you to take this or other projects of your choice through the remaining stages of design thinking that include prototyping, refinement, and presentation of final solution. Knowing how important knowledge of science is to the design thinking process, we now present the following overview of gravity. We all have a base understanding of gravity as the reason this basketball player falls back to the court when he jumps. Gravity is also why the trajectory of a basketball forms a parabola. Gravity is a fundamental interaction of force that causes matter to attract other matter. We commonly model gravity as a field. The closer these fields are, the stronger the attraction force. Let's look at some examples of objects falling to get a better feel for gravity. Imagine you are on the roof of a high-rise building and holding 2 spheres in the air at the same height. One sphere weighs 5 pounds, the other weighs 10. At the same precise moment, you release the 2 spheres. Both spheres begin to accelerate towards the ground. That is, they gain velocity and keep going faster and faster. This acceleration can be measured, and it is constant on Earth, at about 9.8 meters per second square. Or, the velocity of an object increases at about 9.8 meters per second every second. It does this because the Earth is pulling on the object by means of gravity. Many people think that the heavier sphere, or the one with more mass, will drop at a much higher velocity. However, this is not the case. This classic experiment by astronaut Neil Armstrong demonstrates why.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather, for our falcon. And I'll drop the 2 of them here and hopefully they'll hit the ground at the same time. How about that? How about that? Mr. Galileo was correct in his findings.
On Earth, the thing that will change the rate of velocity of a falling object is air resistance. Think of a heavy plane load being dropped from a plane and attached to a parachute. The air resistance on the chute slows down the acceleration. It's important to recognize that weight and mass are not the same thing. The mass of an object is a measurement of the amount of matter, molecular makeup, contained in the object. The unit of measure for mass is the kilogram. Weight, however, is a measurement of force that is affected by gravity. Because the different planets have different masses and radii, their surface gravities vary. By knowing the mass and radius of a planet, we can calculate its surface gravity. The force of gravity on the moon is about 1/6 of the force of gravity on Earth. Therefore, a person who weighs 200 pounds on Earth would weigh 33 1/3 pounds on the moon. When dealing with gravitational forces, it's easier to model these forces acting on a single point of an object. This point is referred to as the center of mass, or the center of gravity. The center of mass is essentially the average point in between all the mass of a body. The rider and bike in this example look like they're performing a gravity-defying feat. However, they can do this because of the addition of a counterweight that has moved the center of gravity below the cable. Determining the center of gravity is a critical factor in the design of many products. In the case of equipment such as front-end loaders, the center of gravity will change depending on how much is picked up and the position of that load throughout the operation. Unless this change in gravity is accounted for, dangerous imbalances could occur, resulting in potentially dangerous accidents where the machine will literally tip over. Tides exist because of gravity. You can imagine tides as the sun's and moon's gravities, pulling on Earth and stretching it. As the Earth orbits the sun and the moon orbits the Earth, these bulges move across the surface of the Earth, causing the tides to rise and fall. In the ocean, these rising and falling modifications can cause currents. Engineers and designers are leveraging the power of these tides to produce renewable energy by means of tidal energy generators. For this unit, the student design project involves creating a device for walking on Mars. Mars's gravitational pull is 3.7 meters per second squared, as opposed to Earth's gravitational pull, which is 9.81 meters per second squared. That means Martian gravity is 38% of Earth's. In order for walking on Mars to feel similar to walking on Earth, a person must carry additional mass. A good analogy would be the weighted belts that divers use to counter buoyancy. In this unit, the student design project involved designing a prototype for a weighted belt that would be used by astronauts to help mitigate muscle and bone density loss due to low gravity environments while exploring Mars. Astronauts would use this belt while inside Mars Habitat Station, where the astronauts would not be wearing the full suit used when exploring or working outside. To begin the design, we will need to know how much additional mass this belt might need to add. If our astronaut has a mass of 70 kilograms, then their weight on Earth is approximately 686 newtons, or 154 pounds. If we use the equation F equals ma, force equals mass times acceleration, while using Martian gravity of 3.7 meters per second squared, we can figure out that on Mars, the astronaut will weigh only 260 newtons, or 58 pounds. If we take the difference between what the astronaut weighs on Earth and on Mars, we can see that they need to weigh 426 newtons, or 95 pounds, more. Once more, by using F equals ma, while using the Martian gravity of 3.7 meters per second squared, we can find out how much more mass the belt would need to add in order to make the astronaut weigh the same while on Mars. In this case, the astronaut will need an extra 115 kilograms in order to weigh the same on Mars as on Earth. Keep in mind, however, that an astronaut's suit has a mass of around 120 kilograms, so no additional mass would be required while they're in a suit in an outdoor environment. However, all the astronauts on Mars would still need this sort of belt while inside the habitat, especially while exercising, in order to keep their bodies healthy.